Oh, hello, Professor. Today I would like to talk about my project. My project name is Research on Supervised Hyperspectral Image Classification Algorithm. My name is Hao Chen. I divided my demonstration into 6 parts. The first part is introduction. The second part is the problem and the study, and the next part is existing approaches, and then is the description of the study approach, and the next part is performance evaluation. The last part is conclusion. So let's start our first part, introduce. Hyperstructure image is a detailed segmentation in the spectral dimension. It's not only the traditional difference between black, white, or RGB, but also have n channels in the spectral dimension. For example, you can divide 400 nanometers to 1000 nanometers into 300 channels. At one time, what we get through the hyperstructure device is a data cube, which not only has the image information, the results can not only get the spectral data of each point in the image, but also get image information of any spectral segments. Hyperspectral imaging technology is based on a lot of narrowband image data technology. It combines imaging technology with spectral technology to detect the two-dimensional geometric space and spectral information of the target and obtain high resolution continuous and narrowband image data. And the second part is the problem and the study. Many typical applications of hyperstructure imaging include severe and biological threat detection, atmospheric environment research, and marine research. The most commonly used technology in these applications is HSI pixel classification, which is called the HSI classification. However, there are many difficulties in HSI classification, especially in processing high-dimensional data and high spatial resolution images. In order to overcome these difficulties, feature extraction methods such as machine learning are applied to HSI classification. Traditional machine learning methods have the same shortcomings in HSI classification, and the classification accuracy needs to be improved. In recent years, deep learning as an alternative to traditional machine learning algorithms have been introduced into HSI classification. They can extract depth, space, and spectral features from hyperstructure data. The application of deep learning to hyperstructure data classification shows that recognition of depth features can improve the classification accuracy of hyperstructure data classification. And that is our existing approaches. In 2014, Chen first proposed the deep learning framework integrating spatial and spectral features. The deep learning framework combines principal component analysis with deep learning architecture. Then the uses stacked automatic encode to obtain advanced features and logical regression to obtain classification results. The framework is abbreviated as SAE-LAR. Although SAE-LAR has shortcomings in training time, it shows that deep learning methods have great potential in HSI classification. And in the past 2 years, Lee has proposed a 3D CNN framework for accurate HSI classification, which directly uses the original 3D high-level data as input without actively extracting HSI features. The framework does not rely on any processing or post-processing, but effectively extracts spatial features and does not distinguish the two features. And that is a description of the study approach. The first part is extracting spectral and spatial features separately from HSI. A 1D CNN extracts spectral features, whereas a 2D CNN extracts local spatial features of pixels. However, HISS contain both abundant spatial and spectral information for HSI classification. This means it's to the use of a 3D CNN, which can extract both types of information, and shown in Figure 1a. The 2D convolution sends a channel of an input image to another feature map after a convolution kernel operation. For an input image with three channels of spectral information, a 3D convolution processes the data from these three channels, use two convolution kernels to obtain two characteristic maps, as shown in Figure 1b. And then is the second part, going deeper with densely connected structures. DenseNet combines the numbers of channels and keeps the value of feature map unchanged. In order to facilitate the downstamping of the framework, DenseNet is divided into several densely connected blocks, which are called dense blocks. There is a transition layer connection between each block. Each layer of DenseNet is directly connected to the input layer and the press layer, forming a hidden depth monitoring. This kind of connection structure reduces the phenomenon of gradient vanishing, so as to build a deeper network. In addition, DenseNet has a regularizing effect of restraining overfitting. The third part is going faster and preventing overfitting. Earlier, early stopping and dynamic learning rates are also used when training a model. Stopping early means that after a certain number of efforts, if the loss is no longer decreasing, the training process will be stopped early. This reduces the training time as well as preventing overfitting. We adopted a variable learning rate because the step size should decrease as the result approaches an optimal value. With a better initial learning rate, the learning rate is hard when the precision does not increase after a certain number of efforts. If precision no longer increases after a certain number of efforts, the learning rate will be reduced by half again and will loop until it is less than the set minimum learning rate. The third part is the fast dense spectral spatial convolution framework. Summarizing the above steps, we have proposed a framework that lends deeper spectral and spatial features while reducing the training time compared to deep learning CNN-based methods. The FDSSC framework is shown in figure. So the next part is performance evaluation. First, the FDSSC framework network only uses a convolution layer and an average polling layer to learn features, and a fully connected layer as a classifier, so that it is an end-to-end framework and reduces high dimensions without complicated feature engineering. Second, because of the densely connected method, the FDSSC network has a deeper structure resulting in extremely efficient performance. Finally, the convergence rate of the model is very fast because of BN and PRELU applied to the FDSSC network and the dynamic learning rate and early stopping. So last part is our conclusion. In this experiment, we randomly select 10 groups of training samples from the KSC, UP, and IN datasets. Experimental results are given in the form mean plus and minus variance. The training and testing time results were obtained using the same computer. The OA, AA, and KAPPA coefficient were used to determine the accuracy of the classification results. The input spatial size is important for the 3D convolution method. Therefore, to ensure a fair comparison, an appropriate spatial size was chosen for each method. For the SSRN method, the classification accuracy increased with the spatial size. So we used an input spatial size of 9 multiplied 9, which was the same as that of the FDSSC framework. Fig 10 to 12 show classification maps for each of the methods. And this is fig 10. And the left map is fig 11. Right map is fig 12. So in terms of accuracy of HSI classification methods, for deep learning based methods, our experiments show that deeper the framework is, the higher the classification accuracy. The proposed FDSSC framework is obviously superior to the SAE-LR, CNN, and SDCNLR methods. Compared with the SSRN method, which has the state-of-the-art accuracy, the FDSSC method improves OA and AA by 0.4 per hundred and 11.23 per hundred, respectively, for the IN dataset. It is precisely because of the greater depth of the FDSSC network that the spectral and spatial features of HRSIS are more effectively utilized, with better feature transfer between the convolution layers. Although the training size of the SAE-LR and CN methods are greater than that of the FDSSC framework, the FDSSC framework has higher accuracy than the SAE-LR and CN methods.